Hey, everybody. Thanks for coming. Thanks for the intro, Blake. I'm James Phillips. I'm the lead developer on Consul. Been at HashiCorp for about a year. I feel really lucky to get to work on Consul. I've been lucky enough over my career to work on things that I still think about or maybe are still in use 10 years later. And I know Consul's one of those things. It has a really cool design. In terms of like coming onto a company and working on a project that already existed, Consul had a pretty nice structure. It's been a lot of fun. So I like what I do at HashiCorp. This may be a little bit of a weird talk. I'll do a really brief introduction to Consul, kind of cover all of its features. And then I'm going to kind of geek out on some lower level parts of Consul that most people don't really understand or get to know about. There's sort of layers of Consul that are sort of under the hood. And then we'll finally get to GEO Failover at the end, I promise. It'll seem like I'm completely ignoring the topic, but we'll get there and it'll all come together. So how many people here have heard of Consul? Sweet. How many people have tried it, played around with it? How many people would get a page if Consul went down? All right. And how many people would, like NASDAQ, would halt trading on your stock if Consul went down? Sweet. All right. That's awesome. That's how. So we'll do a little bit of an introduction. And there may be some newer features that you're not really familiar with. So at a really, really high level, Consul has sort of three main themes. The first one is service discovery, configuration, and orchestration. The second one is monitoring at scale. And the third one is supporting high availability of your applications, in addition to Consul itself being highly available. So we'll go through these three. So sort of our bread and butter is the service discovery, config, and orchestration. For Consul, what a service really means is an IP and a port number for something that's running on a machine someplace in your infrastructure, as well as a set of checks that Consul will run for you to make sure that service is actually healthy and useful to the rest of your infrastructure. You can register via configuration files, so if you have static things that kind of ship with your AMI or are part of your build, those can be just configured with files. And then if you're running a schedule or doing anything dynamic, you can speak to Consul's REST APIs to register services on the fly. You can register your containers, things like that. In terms of getting service information back out, you can discover them via DNS interface or via the HTTP interface. We'll talk about DNS a little more. You can do load balancing without actually having a load balancer because the DNS results are randomized, so you'll get traffic spread across all the healthy nodes in your cluster just by using DNS queries. You have a full KV store, so you can manage other parts of your application configuration that you want to change on the fly via key value. And you can also use the key value for orchestration. You can do locks, you can do leader elections, semaphores, things like that. And then finally, there's a lot of ways to integrate Consul with your existing apps. So the DNS interface, you can do a native integration like Vault and Nomad do, where they actually speak to Consul directly with the API client. We have things like Consul template is like the universal glue to all things. It'll write configuration files out and run scripts. So people have done horrible and awesome things with that. And Consul will plumb into environment variables, so there's a lot of options there. For monitoring at scale, you can run node-specific checks. So those are checks that Consul will run anywhere the Consul agent is running to make sure the machine is healthy. And then as we mentioned before, you can have health checks that are specific to the services that you've configured in Consul as well. They're Nagios compatible script checks, so there's a huge library of open source scripts that you can run. You can run health checks inside of Docker containers. You can hit HTTP endpoints. You can see if you can do a TCP connection. There's a lot of built-in things. And we also have sort of a dead person switch, like a TTL check. So you can register a check with Consul that your application is responsible for poking every once in a while to make sure your service is still healthy. And then for high availability, you can actually connect different Consul clusters together very easily. If you've connected your Consul clusters together, you can query information across clusters very easily, and in some ways we'll see here transparently. And you can coordinate complex distributed systems with Consul primitives, and we'll show some examples of that too. So how does it work? And this is where we'll start to dive into some of the details. So Like all HashiCorp stuff, Consul agent is a single Go binary. It's really easy to deploy. You run the agent on every machine in your data center, and there's a common set of questions on the mailing list, like I don't want to run the agent everywhere, and you want to run the agent everywhere, and now you'll see why. But it's an interesting, your instinct is always like to run the Consul servers and put them behind a load balancer, but then if you run the agent everywhere, your applications can just look locally, and you don't have this sort of turtle zero problem of how do you find Consul itself. So we'll talk about that a little more. Some subset of your agents, usually 3, 5, or 7, are configured as servers. Everything else are client agents. And the servers have sort of a special role in Consul. They maintain a consistent view of the state of the cluster. And when you do things like DNS queries or make key value updates or reads, those end up going sort of behind the scenes up to the servers. And your applications just talk to their local agent. So if you're running the agent everywhere, and you're actually configuring something to hit a key or do a DNS lookup, you just do it against localhost 8500, and it'll talk to Consul. Consul will figure out which server to send things to. It'll figure out if that server's dead, where's another one. All that stuff is managed under the hood. So your application's just statically configured to talk to the localhost, talk to the Consul agent. So here's a picture of all that. So this would be within a single data center. So the boxes on top are the client agents. So like if you're running, VMs and EC2 or whatever, those would just be machines doing stuff for your applications. Maybe one of them's your database, one of them's running some application servers. If you're running a scheduler, maybe those are your Nomad worker nodes, whatnot. So you're running the agent on all those machines. The 3 boxes at the bottom are your servers. One of them is a leader, so there is a consensus algorithm that automatically determines the leader. That's replicating changes out to the other servers. And there's some RPC forwarding in there. We'll talk about that in a little more detail. And LAN gossip, like we always, at HashiCorp we talk about gossip, and blah, blah, but a lot of people have no idea what's actually going on there. So we'll dive into that a little bit. I mean, most people who operate Consul just know I need to open port 8301 for some reason or it doesn't work. And if I don't open TCP as well as UDP, it like kind of works, but then I get these weird errors. So now you'll know why. It'd be cool. So one thing with Consul, actually my coworker before I joined HashiCorp, I told him I'm gonna go work on Consul, and he said, ooh, it's like the Swiss Army knife thing with like health checks, and it's got all this stuff. And that's true, but it incorporates a few tightly integrated pieces for good reason. So, I mean, nobody likes sporks, but if you were camping, this is like a titanium spork. It's a lightweight thing. It's the one thing you need to carry. The handle, you can measure stuff. You could do a tracheostomy with it if you needed to in an emergency. Like, sometimes you have these really thoughtfully crafted tools that combine a few different elements for good reason. So we'll talk about some of those themes. So why did we take our service catalog and build a DNS server into it, right? We could have composed a few different pieces. So first of all, why did we put a DNS interface like Consul at all? It's the zero-touch integration with like anything. You can have your crustiest thing from 10 years ago. You can have a new thing that you just don't want to make aware of Consul in any way. Anything can do a DNS lookup. It's an awesome interface. You configure your app to look up this magic name like foo.service.consul, and it's just gonna work. And since we shuffle the results, it's actually gonna load balance across all available instances of the foo service just by doing a lookup. So it's kind of like the 3.5 millimeter jack of software, right? Like, can you imagine a world where like every manufacturer made a proprietary headphone connector and you had to carry like, exactly. So you have to carry these dongles, and what would the airplane put on there? And the airplanes would have to carry dongles for all the different headphones. And so like, you'd probably burn like another 1 million tons of fuel carrying dongles for headphones. So anyway, all right. So it makes really good sense from a user experience perspective to deploy one thing with the DNS server already in there. And Yeah, Consul's a few millimeters thicker, but the users are okay with that. So, all right. So why did we combine Service Catalog with health checks? There's already Sensu and Nagios and all this stuff, right? Well, if you integrate these things well, the state of the world is as fresh as possible at all times. So if a service failed, we pull it out. We stop returning it in DNS requests. Anybody that's doing like a first-class integration with Consul knows that that service has failed, don't use it. If a whole machine dies, we can pull all the stuff that was running on that node out of service. If you spin up new stuff, you saw Kelsey's talk, he ran 10 more and they were available as soon as they were available. So the humans can sleep, stuff gets pulled out, stuff gets added in, nobody touched anything. So having those integrated deeply is super nice. And there's a reason it's been thoughtfully integrated. It's not a Swiss Army knife. Why would you integrate health checks with your key value store? Well, it's kind of weird, right? Well, you can do things like leader elections with a command like consul lock. So you basically put consul lock in some command, and then you know around a specific key name, and anybody that does that lock around the same key, you'll get one instance running somewhere in your cluster, and if that one dies, another one will get the lock. So you've got leader election with automatic failover within your data center, basically by adding a few things in front of your command line. So pretty amazing. But you need health checks because if the machine dies, you need to know to release that lock. Otherwise, the human has to come in and do a curl-x delete. So by combining the health checks with the KV store, it just works. There's nothing to touch there. So we want you to sleep. We want you to spend time with your family, not delete a key at 3 a.m. All right. So we've mentioned health checks several times here, and they seem to be kind of a critical part of Consul. So let's dive sort of one turtle level down into how Consul does health checks. So we mentioned this before. You can define health checks in Consul that run at the node level. So those are things like watch for disk space, see if I'm running out of memory, see if the network cards failed or whatever. So those would sort of get logically ANDed with all the services running on that node. So if the machine's out of disk and you've determined that's a critical failure level, then it'll pull all the stuff out of service. It won't give that node's IP address to anybody that's asking over DNS. And then Consul has this is this node alive check that it just configures automatically anywhere the agent runs. So Consul keeps track of whether the agent is reachable over the network and if it's responding in a normal way. So for the rest of this talk, we'll be focused on that second type of health check, because there's another turtle level we have to descend now. So a typical traditional health checking sort of pull kind of model has a central thing that reaches out to everything it knows about and pulls for health. So are you healthy? Yeah. What about you? Eh. And you have a single point of success that becomes a network bottleneck. It becomes a single point of failure. It's kind of, if you have 10,000 nodes, it's doing 10,000 TCP round trips all the time. So it works, doesn't scale well. What Consul does is the edges just push changes back to the server when things happen. So you'll have a database, you'll have a health check script fail on one of these nodes, and it'll say, hey, this isn't healthy anymore. So you go from tens of thousands of TCP requests back and forth to a message every once in a while when something comes out of service when it goes back into service. So this is awesome. We had tens of thousands of messages. Now we have a handful. But what do we do when a node dies? Like, what's its last gasp? It may say something interesting. It may wish it had watched more television or something, but it didn't. It's probably not going to say anything. So that is fatally flawed as a plan unless you have some way to tell that a node just dropped out. So Consul has a built-in distributed failure detector. So now we're going down another level. So what is this thing? It's based on a paper titled SWIM, which stands for that. It has some cool things in there, like infection style. So there's some interesting nuances to how it works. We get this through using Surf as a library. Surf is another HashiCorp product that basically just has the membership and failure detector part without the Consul, like health checking and Raft and all the sort of upper layers. And it's interesting, Surf is either, if you look at the mailing list traffic, it's Raspberry Pi, Internet of Things people, like finding all the junk in their house, or there's like 10,000 node supercomputers that are using Surf. And PayPal, I mean, there's like random people using it for really interesting, wide varieties of things, but yeah. But Consul incorporates it as a library. And it uses a small constant level of networking load. So there's an amount of load that scales with the size of your cluster, but it's fixed. And it allows messages to propagate really quickly through this gossip protocol. And it has a distributed failure detector that works at really, really massive scale. So let's talk a little bit more about what a gossip protocol is. So this maintains a shared set of members. So everyone running the agent has some awareness of all the other agents that are out there through this gossip protocol. So kind of this background process that's running everywhere. And the key to gossip is you do all your stuff via a few small messages that you always send to a fixed number of peers. And they may re-forward some of those messages, but you always have sort of a fixed fan out. So even if you have 100 nodes or 10,000 nodes, each of your nodes is going to talk to like 3 other randomly selected nodes at any given time. It's mostly UDP-based, but it does use some TCP, we'll see. And then in Consul, the stuff that comes into the leader server gets fed into the consensus algorithm, and that's what forms your consistent view of the cluster. So gossip may discover that some node is dead, and the other nodes will sort of get an idea of it, but when the leader perceives it, that's when it feeds it into the consensus algorithm, and that's when we'll pull it out of service. So let's see how this works. So these are all nodes. So these would be computers in your cluster running the Consul agent, and basically once a second, each node chooses some other random node in the cluster to probe. So it'll send it a UDP message, are you alive? In the happy path, it will receive an ACK, and so, yeah, we're good. And it'll do that again 1 second later. In the unhappy path, it'll wait for a timeout. If it doesn't receive a response, it'll do a TCP probe back to that member, and it'll also ask a fixed number of other nodes to check that for me. So if A and X had some kind of connectivity problem between them, A could still learn that X is alive through one of the other nodes in the cluster. So, because the consequences of falsely accusing a node of being down are pretty high. Like, we'll pull all the stuff that's running on that out of service. So we really want to be sure. And there's some tunables at the library level that we've chosen to make this reliable. So it's a trade-off between bandwidth and timing and time to discover a failed peer, things like that. The TCP we actually added because so many people got firewall rules wrong and things like that, it just prints a message saying like, you probably haven't set up your ports correctly. So that's mostly why TCP is there. It's also a good, backup check. But it's mostly just to provide a better user experience. So those 2 peers will also send it a probe. And if they don't hear back, they'll send a NAC back to the originator. If X did respond to them, they would have forwarded the ACK back through their path. So it doesn't rely on a direct connection back. It'll go back through those other ones. And the star is there because the NAC is actually new for Consul 07, and I'll talk about what that's for here in a sec. And so this is kind of the fun part. So node A just didn't get a probe. We got 2 NACs, so it gossips out X is suspect. And this kind of gives you a sense for how gossip works. So the A node will pick a few random peers, gossip it out. They'll pick random peers and gossip it out. It's kind of like a TTL in IP networking. So you won't rebroadcast something you've already seen, but as long as it's new to you, you'll start spreading it out. So you'll see like each of those has a limited fan out, And it's super cheap. And we actually, there's a lot of fanciness that's not shown here, where messages get batched and things like that. So there's actually kind of like you can think of gossip as sort of like a fixed frame of all the things you collected over a certain time interval that get blinked out to some random peers. So it's a little more efficient. It doesn't actually cause this spray of packets instantaneously, but I've shown it that way just for simplicity. Then the node that suspected kind of chills for a minute. It waits. There's some time built into the protocol for the accused to refute that they're actually down. But if it doesn't hear back, then it says it's failed. And that goes out over gossip as well. So we have a simulator that's part of the surf website. So I ran it for 10,000 nodes, assuming like 1% of them were failed. You lose 1% of your packets. It would take about 2.5 seconds for that word to get out to all 10,000 nodes. And your sort of fixed bandwidth cost per node would be about 300 kilobits. So that's like what this process would cost you as sort of a fixed amount of low background traffic for a 10,000 node cluster. So, but it's pretty miraculous actually when you see it converge in 2.5 seconds. That's pretty cool. So for Consul 07, we actually we made a lot of improvements to this protocol that are based around the NAC feedback. So one thing that was interesting was in the previous implementation up to 07, there was kind of an assumption that the node doing the probing was good. And what you'd often see is you'd have like kind of like a low-end compute instance, and it'd be out of CPU credits, and then it would just start handing out shenanigans to nodes. It'd be like, you're busted, and you're busted, and you're busted. And it would heal, so they would refute, but depending on the timing, you'd get flaps. And the consequences of accusing somebody falsely are really high. Like if you pull your master database out of service for 2.5 seconds, like that's not good. So what we did was we added feedback based on the NACs. So if it accuses it and it doesn't hear any NAC feedback either, then it starts to say, ooh, maybe it's me, and it'll back off the failure detector rate. And the real cool thing that's kind of subtle here is that it'll start with an initial timeout. So remember when it was doing the little thought bubble? So that used to be kind of a fixed small timeout, and that actually starts out much larger now. But because the node that's failed gets probed by other nodes in the seconds that follow, that timeout will be accelerated if it gets confirmation that other nodes think that that's failed too. So that combination is super, super useful for smoothing out, a bad actor like this. So it'll say like, well, that's suspect, and in 30 seconds I'm gonna declare it failed. And then by that time, it will definitely have had time to refute if it wasn't actually failed. But if over the next 5 seconds, 5 other nodes also say it's failed, then it runs that timer back to 0. So we increased the timeout to this huge 30-second interval, but the detection time for an actual failure stayed the same, which is pretty sweet. That's an Armon like email over Christmas break, like I have this idea, and then it was awesome. So just to have some awesome looking colorful things, like this was a test we did sort of before and after. So we intentionally degraded basically the orange ones, and then the blue ones were ones that got sort of flappy, falsely accused, and then with Lifeguard, we only have the ones that are actually failed, showing up as failed by the rest of the cluster. So now we have a distributed failure detector. So we can have edged triggered health updates without polling, but we can reliably, through this mechanism, figure out that a node's gone down. So let's go like one level down and talk about network tomography. So what's tomography? Like you've probably heard of a CT scanner. So the way that works is you have a thin beam of radiation, and you have a radiation detector, and you point it at your head from various angles, right? So you're getting basically one number from each reading, which is how much radiation you got from here, and you've got this angle and this angle, and through math and stuff, it ends up, the intuitive but not complete explanation of how a CT scanner works is it actually it's almost like smearing that number backwards towards the source. And then when you have enough sort of big, thicky things, the smears will sort of cross over and make that spot darker. But if there was less material in certain spots, it would be lighter because you'd have less sort of intersecting smears of large numbers, but that's getting a little detailed. What's network tomography? So network tomography is taking advantage of, it's the baby carrots of this whole thing. So if you know about baby carrots, they're actually not a real thing. But they used to throw away the ugly carrots, and somebody decided if you cut them up and polish them, you can sell them to little kids. And it's like it's a billion-dollar business from stuff you were just throwing away. So we, through this probe process, if you get an ACK back, you have a round trip time measurement to some random node in your cluster, and you're getting those at 1 hertz from everybody. And we were just throwing those away. So enter network tomography. What this is, similar to the CT scan example, you basically take those round trip time measurements, and instead of making a 2-dimensional picture of a slice of somebody's brain, you're making a model, and we'll talk about what the model looks like. So it's also based on some research. The sort of base paper was something called Vivaldi, and we also used like 3 sort of follow-on studies that had some improvements to this. And the way it sort of works intuitively is you connect all the nodes with springs, and you kind of bunch them up or randomly assort them at the beginning, it doesn't really matter. And then you relax as you learn about the distances to others, the round trip time becomes sort of the natural length of the spring, and you just relax the model. So you kind of let it settle out. And at the end of this process, you get what's essentially a coordinate system for all the nodes in your network. And by doing a simple calculation, you can estimate the round trip time between those nodes. And those nodes don't have to have even ever pinged each other directly. And if you wanted to actually do this with pinging, you'd have this n-squared horrible thing that would never work. And all it adds overhead-wise is to add the coordinate of the node you probed in the ACK. So it adds, I don't know, it was like 60 bytes or something. So, and it's in a UDP message, so it's free. So this is kind of what this process looks like. So initially, you don't know anything about what the round trip times are. And then as these probes happen, they sort of push themselves away from each other based on setting their spring lengths to the round trip time they observed. And then once you've got some existing coordinate information, and then you get another probe from that, you can refine your model. So very quickly, this converges into a model that represents the round trip times correctly. So Armand just gave a talk, Papers We Love talk on sort of all the details here. You end up with an 8-dimensional coordinate system for reasons. We do some filtering. So we do like a really simple like median filtering. So if you get a pop of some long ping every once in a while, it doesn't totally vibrate your model too bad. There's a gravity factor actually, because if you don't, your whole model will kind of drift away, so we pull it back so it's centered around the origin. When you restart a node, it remembers where it was, so you don't put it way back and have to relearn where, that's the snapshot. So there's a lot of improvements, and these are pretty interesting to dig into. But the upshot is you get some coordinates that you can feed into code like this, and this gives you the round trip time between any 2 nodes. And I'm not going to go through this, but it's basically the square root of the sum of the squares of the 8-dimensional thing plus some fudge factors. But that's the code. It's not complicated. If I gave you 3-dimensional vectors, you could find the distance between them. It's very similar to that. And then Consul knows, hey, what's the round trip time to that node? It's 780 microseconds. If you wait a while and ask again, it'll bump around a little bit because it's being updated continuously. Are we here yet? Not quite yet. So now we've got, we have all these features. We've got our health checks. We've got a distributed failure detector. We've got a continuously updated, basically zero overhead, automatically generated model of our cluster. So we know the round trip time between everything. So we're almost ready to do GEO Failover. We've built on these cool academic papers. We need one more thing. We need the actual GEO piece. So we need like multiple consuls. So here's how multiple consoles connect together. So the top is the picture we saw before. The bottom is a cluster somewhere else. So you can think of like the top is in Asia, the bottom one's in the US someplace. Now you know what the land gossip dotted arrow means in the top picture. We use that exact same code and that exact same structure for a separate set of WAN gossip. So when you join two Consul data centers together, you join the servers together and they start gossiping, and they're tuned to much different timing because they're expecting to run over super long links. So they have very, very relaxed timing, but they're building a set of coordinates that represent where all the servers are all over the world. So you've got that information built into Consul. So each data center has a name. Like I said, all those same features are there. When you are part of what we call the WAN gossip pool, we know, now the Consul servers know how to route RPC requests between the different data centers based on the data center name. So if you say, I want this key from this data center, that you're going to forward, your app's going to talk to your local agent. It's going to forward to one of your local servers. It's going to look in the WAN pool and say, oh, that's Asia, send it to that server. And then that'll resolve it within that cluster. So that gets you the connectivity between the clusters. And then for network tomography purposes, we use the median distance to the servers. So we treat the servers as kind of a bucket. So that's that we know that, the US one is 100 milliseconds from Asia because we just take the median round trip time between my chunk of servers and that chunk of servers. So we're almost there. There's one other thing. So prepared queries. This is a new thing in Consul 06, and it has had some enhancements in the sort of point releases that followed that. What these are is you register a prepared query in a particular data center. So there's a namespace for each data center. You define what services to look up and what to do if you can't find anything locally. And you can execute these via the REST APIs, you can execute these via DNS. So here's just some examples. So this one, I even put the curl command. You can just paste that in there and start GEO Failover real soon here. So we're getting there. So this makes a query called Redis. It maps to the service name Redis, and then the failover says nearest N3. So what this means, before we would have looked up something like redis.service.consul, and that would have given us a Redis instance in the local data center. So we changed that to redis.query.consul, and now it runs this thing. And if nothing's available locally, it'll try the next 3 Consul data centers that it knows about based on round trip time. So you didn't have to name them. If Asia goes offline, then it might go to South America or whatever. Like you don't have to care as an operator how to configure that or keep that up to date over time. After 06 shipped, a lot of people said, I love this, but I have 10,000 services and I'm never gonna keep any of this up to date. This is a nightmare. So we added prepared query templates, and I can't even parse the regular expression in real time in a presentation, so I'm not gonna go through that. But what that stuff does is it picks part of the name and maps it into the service name, and then it takes another part of the name and maps it into a tag you want it to have. So the sort of summary of what that query definition does is if you look up something like GeoDB customer master, it'll look for a service called MySQL-customer. So that's like your database name with the master tag on it, and give me that. And same thing, nearest N3, it'll fail over, it'll just do it. And the cool thing, you can only have one of these per cluster, but you can do a catch-all template and just say, take whatever name they gave and stuff it into the service name. So you can register this and it'll give GEO Failover to every service in your cluster by just looking up that.query.consul instead of that.service.consul. So if there isn't one where it checks or you don't have any in other data centers, it'll try and give you an error back or, no, you won't get any servers. But this is just kind of like one thing I'll blanket apply it to all your services. So we finally gave you GEO Failover. So here's like an integrated picture of how all that stuff works. So the left side is maybe a data center over in Asia. The right-hand side is one in the US. So the light purple stuff at the top, these are sort of the things running on a Consul agent somewhere. So the left-hand one is the database. Say this is like a read replica, right? You can just go from wherever. But you want it to be reliable. It's your, I don't know, it's your some kind of important thing to your business. The middle are the Consul clients that are sort of running on the machine where those things are running. And then there's sort of a dark purple set of dots. That's just like other stuff in the cluster in that data center. And then the blue things are the Consul servers. And I'm showing sort of 5 servers in each data center, but one of them is a box, so I can sort of label them better. So the little blue dots are your Consul servers. And what's happening here is, so your app, it just did a DNS query for db.query.consul. So this is like some crusty app. Maybe you don't even know how to build it anymore. But you changed its config file. You made it service discovery aware. So it does a DNS lookup. There's a local instance that Consul gives back, and it connects to the database. So things are looking good. You haven't actually integrated this app with Consul natively. So all it knows is I have a TCP connection to that database now. So let's say that whole machine got taken out of service for some reason. Somebody terminated it accidentally, whatever. So your app's probably gonna experience like a TCP connection error. It didn't do a first-class integration with Consul. All it knows is some config file has something called db.query.consul in it. Independently, the health checks you might have for the database were running, but those don't even matter because the machine's dead. So the LAN gossip on the left there is going to figure out that node is dead where the database was. It's going to gossip that out. The node failed. Gossip is going to reach the Consul server. It's going to say, oh, the database was running on that. We're going to mark all the services down that were running on that. So if you ask again, you're not going to have a local database available. So, but all the app knew was, hey, I got some TCP error. I'm going to try again. So it's going to go back, do a reconnect. There was a 0 TTL in that DNS entry that result that it got back. So it's going to reconnect. I want to connect to db.query.consul. Where's that? And it's going to go to its local Consul agent. There aren't any available. So now you see the RPC request off to the US here. And if you look at the WAN gossip there was a median round trip time of 111 milliseconds to our Consul server in the US, and it was 129 to South America. So we want the US one. It's going to get the address of the one up there, and the app's going to connect to that automatically. So, I mean, if you look at the amount of stuff underneath your app that's doing stuff, it's pretty amazing. But your app just did a DNS lookup, so your app didn't know anything past like glibc or whatever. It didn't know anything about any of this. And as an operator, you really didn't have to know much about any of that either, other than you trust it to work. But there's quite a few layers that are interacting here to make this all possible. So wrapping up, this is the made easy part. So it's basically just one slide. So in your, before you ever had Consul, you probably, in your config file for your app, you probably had some host thing. If you were really gross, you had an IP address in there. So you didn't even know what the name of the thing was. Say you brought in Consul to one data center, started playing around. Ooh, we got db.service.consul, and we manage it, and it's got health checks, and if we can read, hey, it's a read replica, just run 5 of them, spin up some more. The health check will tell it when it's caught up and mark it healthy. Apps will start talking to them. And then for GEO Failover, you just change service to query, and you curl that one thing beforehand. So pretty good. And I think you'll see this as a theme across a lot of HashiCorp products. And it makes them a pleasure to work on. There's some underpinnings that are based in research that are sort of thoughtfully applied and provide really, really good foundation for these higher level features. So we had the distributed failure detector, so we had a scalable health checking system. which let us tie the health checking system into service discovery in a first-class way, which provided this. I mean, I kind of made it sound like it was an accident, like, oh, baby carrots. But there was some thoughtful design saying, hey, we're going to have a full coordinate map of all the machines in the cluster and worldwide. So that leads to nearest neighbor failover. Even within your data center, you can find the closest instance of whatever you probably can get on a rack, or there's a lot of stuff there. But it's built on a really good foundation. So this wasn't like we had to go retrofit or rip out it. It layers super nice. And you can basically do full deep integrations, like Vault and Nomad talk to HTTP directly to the Consul agent and register themselves and add their own health checks and manage their TTLs. And all your other stuff can work via DNS, and it can access all the same stuff. So thank you. I'm Slackpad on the internet. The Consul mailing list in GitHub has a lot of information if you're kind of just getting used to Consul. And if you're interested in the specific stuff we talked about, I put some links up here to our internals guide for gossip, how network coordinates work, and then prepared queries is kind of a lot of people aren't aware of that. It's kind of a sleeper feature, but we're trying to get the word out on that. So thank you.